Forget black holes. Forget the empty void between galaxies. The darkest object with a measurable surface ever discovered is a planet, not a place where light cannot escape, a real world orbiting a real star with an atmosphere, a temperature, and a year that lasts just 59 hours. Coal reflects about 4% of the light that strikes it. Black acrylic paint reflects around 3%. This planet reflects just 0.04%. It is not slightly darker than coal. It is roughly 75 times darker. That should not make sense. The planet circles just 3.1 million miles from its parent star, so close that it is flooded with starlight every moment of its existence. Yet almost none of that light ever comes back. Instead, the planet absorbs nearly all of it. The heat is so intense that the world produces its own faint crimson glow, like the last ember left in a dying fire. In 2011, NASA's Kepler Space Telescope confirmed every one of these measurements. The observations survived repeated checks. The calculations held. The paper was published, but the conclusion was deeply unsatisfying. No existing atmospheric model could fully explain what they were seeing. More than a decade later, that mystery remains, and the darkness may not even be the strangest part. Astronomers know many of the chemicals present in the planet's atmosphere. They have modeled how those chemicals should interact with light. The numbers still refuse to add up. Something else appears to be hiding there, something absorbing photons with an efficiency that current planetary physics struggles to explain. What do we actually know about the atmosphere of TRES 2b, and why does it fail to account for a world this dark? What are the three leading scientific explanations competing to solve the mystery? What does the interior of a planet like this look like, layer by layer, beneath an atmosphere that swallows almost every ray of light? Why could the Kepler telescope measure the darkness so precisely, yet remain unable to explain its cause? And what might newer observatories finally reveal? Let's talk about what we actually know. Imagine standing beneath a clear night sky, knowing almost every point of light could host worlds we cannot see. We call those distant worlds exoplanets, a simple name for any planet that travels around a star beyond our own sun. The idea sounds familiar today. It was anything but certain for most of human history. For generations, we believed other planetary systems probably existed. Belief, however, is different from evidence. Before 1992, astronomers had not confirmed even one exoplanet. Every model, every calculation, and every hopeful prediction rested upon indirect reasoning. But the first confirmed discovery arrived from an unexpected place. Circling a pulsar, the rapidly spinning remains of a collapsed star called a neutron star. Instead of finding planets around a peaceful sun-like star, researchers found them around one of the strangest objects known in the universe. That single discovery changed astronomy forever. More detections gradually followed. By 2011, when the remarkable darkness of TRES 2b became firmly established, scientists had identified roughly 700 confirmed exoplanets. Today, that number has grown beyond 5,700. Each one expands our picture of what planetary systems can become. Finding these distant worlds remains remarkably difficult. A planet produces very little visible light of its own. Its parent star shines so intensely that the planet disappears within the glare, much like trying to notice a drifting speck beside a powerful searchlight. Direct images are therefore extremely rare. Most exoplanets reveal themselves through careful measurements rather than photographs. One technique transformed the search. It is called the transit method, meaning astronomers watch for a planet crossing the face of its star from our viewpoint. During that crossing, the star becomes ever so slightly dimmer. The change is tiny, yet it repeats with remarkable consistency. That recurring decrease becomes the unmistakable signature of an orbiting world. A major leap arrived with the Kepler Space Telescope, launched during March of 2009. Instead of sweeping across the heavens, it fixed its attention upon a single region containing about 150,000 stars. Day after day, it measured their brightness with extraordinary precision, searching patiently for those repeated flickers. TRES 2b had already entered astronomy before that mission began. It was discovered during 2006 through the Transatlantic Exoplanet Survey, a network of modest ground based telescopes working together across different locations. Kepler then became the instrument that revealed far more about its unusual character. Its home lies within Draco, the ancient constellation named after the dragon of Greek mythology. Roughly 750 light years away, that is about 4,410 trillion miles, one faint star held a world unlike any previously measured. But as Kepler gathered increasingly precise observations, the recorded brightness refused to behave as expected, and the numbers themselves began telling an extraordinary story. The mystery emerged from a pattern so small that no human eye could ever notice it alone. Hidden within years of precise observations, tiny changes in brightness carried information far beyond the moment of a planetary transit. They revealed how an entire world behaved throughout every stage of its journey around its star. David Kipping, working at the Harvard Smithsonian Center for Astrophysics, joined with David Spiegel from Princeton University to study what astronomers call a phase curve. A phase curve records how the combined light from a star and its planet changes across one complete orbit. As TRES 2b circled its star, different portions of its illuminated hemisphere turned toward Earth, much like the changing appearance of our own moon. By measuring those subtle variations, they could estimate how much starlight the planet reflected back into space. The calculation seemed straightforward. Existing models predicted that a gas giant with TRES 2b's size and intense heat should still reflect a modest amount of incoming light. The expected value was only a few percent. Even so, that amount would leave a detectable signature within the observations collected by the Kepler Space Telescope, but the numbers refused to cooperate. Instead of matching theoretical expectations, the reflected light almost vanished. The measurements indicated a reflectivity below 1%. That result alone was startling because the planet appeared roughly 3 to 5 times darker than atmospheric models anticipated. Then the best fitting solution pushed the mystery even further. Its geometric albedo, the scientific term describing the fraction of light reflected directly back toward an observer, settled near 0.04 of 1%. That value approached an almost unimaginable level of darkness. Extraordinary claims demand extraordinary care. Every calculation was examined again. Instrument performance was checked for hidden errors. Independent observations from the Kepler mission were compared against one another, searching for any overlooked source of uncertainty. But each review pointed toward the same conclusion. The signal remained consistent. During 2011, the team published its findings in the monthly notices of the Royal Astronomical Society. The result entered the scientific record with careful language and detailed analysis. Publicly, David Kipping described TRES 2b as considerably less reflective than black acrylic paint. He also called it truly an alien world. Those words captured the growing realization that this planet occupied unfamiliar territory, but the deepest concern reached beyond a single surprising measurement. Planetary atmospheres had been modeled for years using known physics and established chemistry. Those models explained many hot giant planets with remarkable success. TRES 2b resisted that framework. The known ingredients could not absorb enough visible light to produce such an exceptionally low reflectivity. Something within the atmosphere appeared to be interacting with incoming photons in ways the existing calculations failed to reproduce. We were no longer looking at an unusual observation alone. You were witnessing a genuine gap between prediction and reality, measured with remarkable precision and still waiting for its full explanation. Some worlds challenge our understanding through a single extraordinary characteristic, others reshape an entire category. TRES 2b belongs to the second group because before we can understand its darkness, we first need to understand the unusual family of planets it calls home. Astronomers place it among the hot Jupiters, a class of giant planets that circle astonishingly close to their parent stars. Their orbits lie within 1/10 of an astronomical unit, meaning 1/10 of the average distance between Earth and the Sunday Jupiter. By comparison, travels about 5.2 astronomical units from our Sunday. That enormous difference changes everything about how these planets behave. TRES 2b follows an even tighter path. It circles its star at roughly 35 thousandths of an astronomical unit, equal to about 3.1 million miles, which is about 5 million kilometers. One complete year there lasts only about 2.47 Earth days. Around that brief orbit travels a planet with about 1.2 times Jupiter's mass and approximately 1.27 times Jupiter's radius. It is unmistakably a gas giant. Only its surroundings are unfamiliar. Its parent star carries the catalog name Golf Sierra Charlie 03549 02811. It is a yellow dwarf star, broadly similar to our own Sun, although slightly cooler and somewhat less massive. From the planet's perspective, however, that modest difference offers little relief. The distance between star and planet dominates every aspect of the environment. But this arrangement presents a deeper puzzle. Planetary formation models indicate that giant planets should form far from their stars, where temperatures remain low enough for gases and icy materials to collect into massive worlds. Near a young star, that building material cannot survive in the same way. The leading explanation suggests that hot Jupiters formed much farther out before gradually migrating inward over millions of years through gravitational interactions with the surrounding disk of gas and dust. By the time that migration ended, TRES 2b occupied one of the harshest planetary environments known. Its dayside rises beyond 1,000 degrees Celsius or 1,832 degrees Fahrenheit. Those temperatures can vaporize several metals. Liquid water cannot exist under such conditions. Familiar atmospheric chemistry also disappears, replaced by reactions almost unknown within our own planetary neighborhood. Hydrogen and helium still dominate the planet, just as they do inside Jupiter. But intense heating changes how those gases interact with heavier elements suspended throughout the atmosphere. Entirely different compounds can remain stable, while others never have the opportunity to form at all. Another consequence follows naturally from such an intimate orbit. Gravity gradually forces the planet into tidal locking, meaning one rotation matches one complete orbit around its star. The same hemisphere always faces the daylight. Many hot Jupiters display remarkable behavior, but TRES 2b reaches beyond remarkable. Even among these already extraordinary worlds, its astonishing darkness remains the farthest edge of what current planetary science has been able to measure. Time itself shapes this planet in an unusual way. Every orbit, every rotation, and every passing age have settled into perfect agreement, leaving TRES 2b locked in a gravitational rhythm that has likely endured for billions of years. This state is called tidal locking. It occurs when a planet rotates once during exactly the same period required to complete one orbit around its star. As a result, the same hemisphere always faces the star, while the opposite hemisphere never turns toward it. You already know a familiar example. Our own moon keeps the same face pointed toward Earth through this very process. For TRES 2b, one rotation lasts about 2.47 Earth days. One orbit lasts exactly the same amount of time. The consequence is permanent orientation. One side remains beneath constant starlight. The other never receives a sunrise. The day side exists beneath relentless radiation. Temperatures climb beyond 1000 degrees Celsius, or 1832 degrees Fahrenheit. That hemisphere has never known evening. It has never cooled beneath a lengthy night. From the planet's earliest history, the star has remained fixed in the same sky. But the opposite hemisphere tells a very different story. Across billions of years, no direct starlight has ever reached that side. Its darkness comes from geometry rather than the mysterious chemistry we have been exploring. Even so, the night side does not resemble the frozen landscapes we might first imagine. Observations from the Kepler Space Telescope revealed something unexpected. Heat travels efficiently through the atmosphere, reducing the contrast between day and night. Estimates place the night side near 1300 to 1500 Kelvin, equal to roughly 1027 to 1227 degrees Celsius, or 1881 to 2241 degrees Fahrenheit. That transfer of energy depends upon extraordinary winds. Atmospheric circulation carries heat away from the blazing hemisphere through immense equatorial jet streams. These fast-moving currents race around the planet at several thousand kilometers per hour, which is about several thousand miles per hour, redistributing energy with remarkable efficiency despite the permanent divide between light and darkness. Between those hemispheres lies the terminator, the permanent boundary separating day from night. Along this narrow ring, the star never rises higher into the sky and never slips below the horizon. Every moment repeats the one before it. But this circulation carries more than heat alone. If scorching gases continually spread around the globe, then the unusual light-absorbing chemistry almost certainly travels with them. The atmospheric layer responsible for swallowing incoming light would not remain trapped beneath the blazing hemisphere. Instead, it could surround nearly the entire planet, wrapping both faces within the same remarkable envelope. That idea changes our perspective. The hemisphere facing away from the star has remained without direct daylight since long before Earth held complex life. You and I can imagine a long night, yet this world measures darkness on the scale of planetary history, while intense heat continues flowing across its unseen sky without interruption. Instead of crossing the immense distance between stars, we allow light to make the journey for us. Every time TRES 2b passes in front of its parent star, a small portion of starlight filters through the planet's upper atmosphere before continuing toward Earth. That technique is called transmission spectroscopy, meaning scientists study how gases remove specific colors from the passing light. Each missing color becomes a chemical fingerprint, revealing substances that no spacecraft has ever touched. Those observations show that TRES 2b is built upon familiar foundations. Like Jupiter, its atmosphere consists primarily of hydrogen and helium. Those lightweight gases dominate its enormous volume. But they are only the beginning. Mixed among them are much rarer ingredients, and those trace compounds hold the greatest importance for understanding why this world absorbs so much light. One confirmed contributor is vaporized sodium. Under the tremendous heat surrounding the planet, sodium exists as a gas instead of a solid metal. It readily absorbs visible light, especially across the yellow and orange portion of the spectrum. Every absorbed photon reduces the amount of light escaping back into space. Potassium behaves in much the same way. This element absorbs across broad regions of visible light, extending strongly into the red wavelengths. Together, sodium and potassium create an atmosphere that naturally appears darker than many other giant planets. Their combined influence has been recognized for years in studies of hot Jupiters. But there is another detail hidden within those absorption patterns. Astronomers refer to the broad wings of the sodium and potassium D lines. These are expanded regions surrounding the strongest absorption features produced by each element. Under the intense pressures found inside hot Jupiter atmospheres, those features widen dramatically, allowing the gases to block light across much larger portions of the visible spectrum than they would under gentler conditions. TRES 2b appears to represent one of the most extreme examples yet measured. Another important ingredient is missing rather than present. Jupiter reflects a significant amount of sunlight because bright ammonia clouds cover much of its upper atmosphere. TRES 2b is simply too hot for such clouds to exist. Temperatures remain far beyond the point where ammonia could condense into reflective crystals. Without those brilliant cloud layers, one of nature's most effective planetary mirrors disappears entirely. Researchers also examined gaseous titanium oxide, a compound capable of absorbing large amounts of visible light in extremely hot atmospheres. Early explanations suggested it might account for much of the planet's unusual darkness, but David Kipping and David Spiegel ultimately favored models that excluded heavy titanium and vanadium compounds because such dense materials would probably settle downward instead of remaining suspended high above the planet. Even after combining sodium, potassium, missing ammonia clouds, and intense atmospheric heating, the calculations remain incomplete. The predicted reflectivity still falls well above the measured value of roughly 0.04 of 1%. We can identify several important pieces of the puzzle. Yet the complete picture continues to resist every careful attempt to assemble it. Scientific mysteries rarely end with a single explanation. More often, they become conversations that continue across laboratories, observatories, and decades of careful investigation. TRES 2b now occupies exactly that place. Researchers broadly agree that its darkness is real. They disagree about the process responsible for creating it. One possibility begins with a simple admission. We may be missing part of the chemistry. Transmission spectroscopy has revealed important atmospheric ingredients, yet every observation has limits. Some compounds could exist in amounts too small for present instruments to identify with confidence. Others may form only under conditions so extreme that atmospheric models have never predicted them. If one or more unknown light-absorbing substances fill the upper atmosphere, they could account for the missing reflectivity. This idea remains the most open-ended and perhaps the most humble, because it accepts that nature may still hold chemistry we have not fully recognized. But another explanation focuses less on individual molecules and more on tiny suspended particles. Intense radiation striking a scorching atmosphere can trigger chains of chemical reactions that build complex hazes. These are known as photochemical hazes, meaning layers of microscopic particles created when energetic light transforms atmospheric gases. Saturn's moon Titan displays hazes produced through very different chemistry under much colder conditions. TRES 2b would create them in an environment almost impossible to compare directly. Even so, widespread haze particles could absorb enormous amounts of visible light before it ever escaped into space. A third proposal remains closer to what we already know. Instead of introducing unfamiliar chemistry, it suggests that sodium and potassium simply behave more powerfully than current calculations predict. Under the crushing pressures of a hot Jupiter atmosphere, the broad absorption regions surrounding their strongest spectral features may spread farther than expected. Those widened regions could overlap, covering much more of the visible spectrum together than either element could manage alone. In that case, the mystery would reflect an incomplete atmospheric model rather than an undiscovered substance. But none of these ideas has earned confirmation. Each explanation demands observations with finer spectral detail than previous instruments could provide, or theoretical models specifically designed for environments as extreme as TRES 2b. Existing evidence points in several promising directions without clearly selecting one. That is why the James Webb Space Telescope carries such importance. Its remarkable sensitivity in the near-infrared and middle-infrared portions of the spectrum allows it to search for chemical fingerprints that remained beyond the reach of the Kepler Space Telescope. Trace compounds hidden from earlier observations may finally become visible through those measurements. For now, the scientific position remains refreshingly direct. The atmosphere of TRES 2b absorbs far more light than current theory can completely explain. The landmark study that established this extraordinary darkness closed with uncertainty rather than certainty. Years have passed since then, and that central question continues to stand, inviting better observations, stronger models, and a deeper understanding of worlds, unlike anything within our own solar system. Long before we understood why this planet reflects so little light, another detail stood waiting inside the data. TRES 2b is not completely black. Across the immense distance separating its star from our telescopes, it reveals the faintest trace of its own glow. That glow comes from an entirely different physical process than reflection. Reflected light is simply starlight that strikes a planet before bouncing back into space. Thermal emission is something else altogether. It is light generated by the planet itself because of its temperature. The two phenomena can appear together, yet they originate from completely different sources. Across the dayside, temperatures remain above 1,000 degrees Celsius, or 1,832 degrees Fahrenheit. Much of the night side also stays extraordinarily hot because atmospheric circulation carries energy around the globe. Under those conditions, TRES 2b produces its own thermal radiation. Most of that energy leaves the planet as infrared light beyond the range of human vision. Even so, a small portion extends into the deepest visible red, giving the planet the appearance of a faint ember suspended in space. This behavior follows a principle known as black body radiation. A black body is an ideal object that absorbs and emits energy according to its temperature alone. Every object above absolute zero releases electromagnetic radiation. As temperature rises, the peak of that radiation shifts toward shorter wavelengths. At the temperatures reached by TRES 2b, the strongest emission remains within the infrared, but the distribution stretches far enough that a dim red glow becomes physically unavoidable. David Spiegel described the appearance with memorable precision. He compared it to a burning ember or the coils on an electric stove. That comparison reflects the underlying physics rather than poetic imagination. The planet shines because it has become intensely hot, not because it has somehow escaped the darkness surrounding it. But this glow also complicated the observations. The Kepler Space Telescope did not measure reflected light by itself. Every observation contained two overlapping signals. One came from starlight, returning from the atmosphere. The other came from the planet's own thermal emission. Untangling those contributions demanded careful mathematical modeling because even a small error would change the calculated reflectivity. The astonishingly low albedo depended upon correctly separating those two sources of light. Throughout every orbit, the balance between reflection and thermal emission changes in predictable ways. As different regions rotate into view, the combined brightness rises and falls across the complete phase curve. Those variations contain nearly everything we know about the planet's atmosphere and its interaction with incoming radiation. What finally emerges is unlike the image most of us imagine when we hear the word planet. TRES 2b would appear as a barely visible, deep red point surrounded by darkness almost equal to its own. Its heat becomes its only unmistakable signature, allowing a distant world that rejects nearly every incoming photon to announce its presence through light created from within. Behind every remarkable discovery stands an instrument built to notice what human senses never could. The Kepler Space Telescope was created for exactly that purpose, watching distant stars with unwavering patience until the smallest changes revealed entirely new worlds. The observatory began its journey on March 7th, 2009, launched aboard a Delta II rocket. Rather than circling Earth, it entered an Earth-trailing orbit around the Sunday. This path allowed it to avoid repeated passages through Earth's shadow, giving the telescope an uninterrupted view for months at a time. Continuous observation was its greatest advantage. Its attention remained fixed upon a single region of the sky, stretching across parts of the constellations Cygnus and Lyra. That field covered roughly 115 square degrees and contained an immense concentration of stars, similar to our own Sunday. Astronomers selected this region because many planetary systems there were favorably aligned for the transit method, increasing the chances that distant planets would regularly cross in front of their stars from our perspective. At the heart of the spacecraft sat an extraordinarily sensitive photometer, an instrument designed to measure brightness with astonishing accuracy. It could detect changes as small as about 20 parts per million. In practical terms, that precision allowed it to recognize an Earth-sized planet passing across a Sun-sized star, even from a distance of roughly 750 light-years. TRES 2b already occupied this field before the telescope ever left the ground. Because it had been identified earlier through the Transatlantic Exoplanet Survey, it became one of the first known transiting planets available for Kepler's detailed observations. That fortunate timing transformed it into one of the mission's most carefully examined targets. But the greatest discovery emerged only after hundreds of complete orbits had been recorded. Rather than studying a single transit, researchers combined measurements gathered across the entire orbital cycle. Every slight rise and fall in the system's brightness became part of the phase curve. By integrating those subtle variations over many repeated observations, astronomers isolated both the planet's reflected light and its own thermal emission. Only a space telescope capable of uninterrupted precision could reveal signals so remarkably faint. Ground-based observatories had never achieved that level of consistency. Earth's atmosphere blurs incoming starlight. Daylight interrupts observations. Clouds arrive without warning. Kepler escaped all three limitations, allowing brightness changes far smaller than previous instruments could reliably measure. But even this extraordinary mission eventually encountered difficulty. During 2013, the spacecraft lost its second reaction wheel, one of the devices responsible for maintaining extremely precise pointing. Engineers adapted the remaining systems into the extended Kepler 2 mission, allowing valuable observations to continue before the telescope finally exhausted its fuel and retired during October of 2018. Across its operational lifetime, Kepler confirmed 2,662 exoplanets. Among them, TRES 2b remains one of its most provocative achievements, a distant world that challenged established planetary theory through measurements precise enough to reveal something nobody had anticipated. For a moment, we need to step away from planets and think about something even more fundamental. The mystery surrounding TRES 2b cannot be understood until we understand what light actually is, how it travels across space, and what occurs during the instant it encounters matter. Light is a form of electromagnetic radiation, energy carried through space by linked electric and magnetic fields that continually support one another as they move. The visible colors our eyes detect represent only a narrow portion of a much broader electromagnetic spectrum. Visible light spans wavelengths from roughly 380 nanometers, appearing violet, to about 700 nanometers, appearing red. Beyond those limits lie infrared radiation, ultraviolet radiation, radio waves, and many other forms of electromagnetic energy that remain invisible without specialized instruments. When that light reaches a planet, several different outcomes become possible. Some photons bounce away, others pass through an atmosphere, many disappear into the material itself. Astronomers describe the reflected portion with a quantity called albedo, meaning the fraction of incoming light returned towards space. A perfect mirror would have an albedo of 1, reflecting all incoming light. A perfectly black object would have an albedo of 0, reflecting none. Our moon reflects about 12 hundredths. Earth reflects roughly 3 tenths. TRES 2b falls near 4 ten-thousandths, placing it astonishingly close to complete absorption. Light that is not reflected does not simply vanish. Instead, its energy transfers into the material it encounters. That absorbed energy becomes heat, increasing the temperature of the atmosphere or surface that captured it. This process helps explain why exceptionally dark objects often become warmer than brighter ones exposed to the same source of illumination. For TRES 2b, that effect may reinforce conditions already driven by its intense proximity to its parent star. The process begins on an even smaller scale. Every molecule contains electrons arranged within specific energy levels. When a photon arrives carrying exactly the right amount of energy, an electron can move into a higher state by absorbing that photon. Different molecules possess different energy gaps, meaning each one absorbs particular wavelengths while allowing others to continue onward. This selective interaction forms the foundation of spectroscopy, the technique that lets us identify distant atmospheric chemistry through missing portions of the observed light. But the atmosphere of TRES 2b demands something far more extreme than isolated absorption features. To produce such an extraordinarily low albedo, the atmosphere must remove photons across almost the entire visible spectrum at the same time. It cannot absorb only narrow bands of color. The process must extend broadly, efficiently, and with remarkable consistency across nearly every visible wavelength reaching the planet. That requirement is exactly what continues to challenge atmospheric models. We understand how individual compounds interact with light, explaining how one distant atmosphere accomplishes this level of nearly complete absorption remains one of the most demanding puzzles in modern planetary science. Long before astronomers began debating the chemistry of TRES 2b, another possibility entered the story. The planet itself may belong to a more complicated family than first imagined, one shaped by more than a single star and a single orbit. A study published in 2008 examined the system in greater detail and concluded that the host star might possess a stellar companion. If confirmed, the TRES-2 system would be a binary star system, meaning two stars would be gravitationally bound while traveling through space together. We often picture stars existing alone, yet the universe frequently chooses another arrangement. This possibility is far from rare. Roughly half of all Sun-like stars belong to binary or multiple star systems. Rather than simplifying planetary motion, an additional star introduces layers of gravitational influence that can unfold across millions or even billions of years. The presence of another distant star does not necessarily disrupt a planet immediately, but it can gradually reshape an entire planetary system through repeated gravitational interactions. The proposed companion received the designation TRES, 2 capital letter B, distinct from the planet TRES, 2 lowercase letter b. Observations suggested an angular separation corresponding to a physical distance of several hundred astronomical units from the primary star. An astronomical unit is the average distance between Earth and the Sun, providing astronomers with a convenient scale for comparing planetary systems. At such an enormous separation, the companion would contribute very little direct heat or light to the planet. Its gravity, however, could still matter. Astronomers have long studied a process known as Kozai-Lidoff oscillations. This mechanism describes how a distant companion gradually alters the shape and tilt of another object's orbit through persistent gravitational influence. The changes occur remarkably slowly, accumulating across immense stretches of time. For hot Jupiter planets such as TRES 2b, this process offers one possible explanation for how a giant world formed far from its star before eventually migrating inward until it settled into the scorching orbit we observe today. But that journey may have left lasting consequences. A migration shaped by complex gravitational interactions could also influence the planet's atmospheric evolution. As the orbit changed, the amount of stellar radiation reaching the atmosphere would have changed as well. Temperatures would shift, chemical reactions would evolve, and some compounds might disappear while others emerged. The atmosphere we measure today may preserve evidence of that long history rather than reflecting only present conditions. Even so, an important uncertainty remains. The proposed stellar companion has not been definitively confirmed as a true gravitational partner. It may instead be an unrelated background star positioned along nearly the same line of sight from Earth's perspective. Distinguishing between those possibilities requires precise measurements collected over many years. That uncertainty reaches beyond orbital mechanics. The full history of TRES 2b depends on whether another star has been influencing its path across cosmic time. Until that question is resolved, the origin of its extraordinary atmosphere, and perhaps even the source of its astonishing darkness, remains only partly written. For many years, the broad outline of planetary formation appeared reassuringly straightforward. Around a young star, a wide disk of gas and dust gradually assembled new worlds. Close to the star, intense heat favored the formation of small, rocky planets. Farther away, where temperatures fell low enough for gases and frozen compounds to accumulate, giant planets could grow. The picture seemed complete, and many astronomers believed the essential framework had already been established. Then everything changed. In 1995, Michel Mayor and Didier Queloz announced the discovery of 51 Pegasi b, the first confirmed hot Jupiter orbiting a Sun-like star. This enormous planet completed one orbit in only 4.23 days. Instead of circling at a great distance like Jupiter, it remained astonishingly close to its parent star. The discovery challenged decades of expectation, and in 2019, the two astronomers received the Nobel Prize in Physics, due in large part to that revolutionary finding. The surprise ran deep. According to the prevailing theories of the time, a gas giant simply should not have formed in such an intensely heated region. There was too little cool material available for a massive atmosphere to develop. The observations were convincing, yet the theory could not accommodate them. Astronomers were forced to reconsider one of the most fundamental assumptions about how planetary systems evolve. But a new explanation gradually emerged. Researchers proposed that giant planets might indeed form far from their stars, exactly where earlier theories expected. Afterward, they could slowly drift inward while embedded within the young protoplanetary disk. A protoplanetary disk is the broad, rotating cloud of gas and dust surrounding a newly formed star. As a massive planet interacts gravitationally with that surrounding material, it can exchange angular momentum and migrate toward the star. This process became known as Type II migration. Once the surrounding disk dispersed into space, the inward journey would end, leaving the planet permanently locked into its final orbit. The revised picture solved one puzzle. It also created new expectations. Early migration models suggested that hot Jupiters should appear around a modest fraction of Sun, like stars. Observations from the Kepler Space Telescope later showed that they orbit roughly 1% of such stars, lending strong support to the migration hypothesis. Atmospheric models also predicted these worlds would possess measurable reflectivity because their extreme temperatures should produce chemical mixtures with reasonably understood optical behavior. But TRES 2b refused to cooperate. Its atmosphere reflected vastly less light than those refined models anticipated. Even after accounting for known absorbers, extreme heat, and the absence of bright cloud layers, theoretical predictions remained substantially brighter than reality. TRES 2b occupied territory beyond the darkest outcomes that many standard atmospheric calculations could reproduce. That distinction matters. We are not examining a curious member of a familiar family. We are examining an outlier within a class of planets that already overturned accepted ideas. Each improvement in planetary theory has brought astronomers closer to understanding hot Jupiters, yet TRES 2b continues to mark the boundary where confident explanation gives way to unanswered physics. Stepping back from a single world reveals a broader pattern across the growing catalog of exoplanets. As more distant atmospheres have been measured, astronomers have found that many hot Jupiters reflect surprisingly little starlight. Darkness, it turns out, is common within this family of giant planets. Yet even against that backdrop, TRES 2b continues to occupy a category almost entirely by itself. One comparison stands out immediately. WASP 12b is another intensely heated gas giant with a measured albedo of approximately 0.064. That makes it a remarkably dark planet, yet it still reflects far more light than TRES 2b. Its story carries another extraordinary detail. Gravitational forces from its nearby parent star are gradually pulling the planet apart, and current models suggest it may be consumed within the next few million years. Even under those violent conditions, its atmosphere remains noticeably more reflective than the world we have been following. Another famous example expands the picture. The planet known as Hotel Delta 209458b, often called Osiris, became one of the first exoplanets whose atmosphere was detected directly. Observations revealed hydrogen, oxygen, and carbon escaping from its upper atmosphere into surrounding space. Atmospheric escape is the gradual loss of gas into space as energetic particles and intense radiation overcome a planet's gravity. Its albedo is also low, matching expectations for a hot Jupiter, but it still does not approach the extraordinary darkness measured for TRES 2b. Then there is WASP 76b. This planet has become famous because temperatures on its permanent day side grow high enough to vaporize iron. Powerful atmospheric circulation carries that iron vapor toward the cooler hemisphere, where it condenses and falls as liquid iron droplets. The image is astonishing, yet the scientific lesson reaches further. Hot Jupiter atmospheres are capable of chemical behavior unlike anything found within our own planetary system. But even among these remarkable worlds, a pattern emerges. Atmospheric surveys increasingly show that hot Jupiters generally possess low reflectivity. Extreme heat removes bright cloud layers and favors compounds that absorb incoming light. Even so, the measured values form a broad distribution rather than clustering near complete darkness. TRES 2b lies at the very edge of that distribution, separated by a substantial margin from the rest of the known population. That separation carries important meaning. If ordinary hot Jupiter chemistry fully explained its appearance, astronomers would expect at least a handful of comparable planets. Instead, TRES 2b remains an exceptional outlier. The familiar effects of sodium, potassium, and intense heat appear to describe only part of the picture. We are therefore left with a more focused mystery. Something about this planet itself, whether its atmospheric composition, its evolutionary history, or conditions deep within its interior, appears to be pushing the physics beyond what scientists currently expect. The unusual darkness is no longer merely a characteristic. It has become evidence that another piece of the story has yet to be uncovered. Our attention now turns beneath the atmosphere, below the layers that absorb nearly every trace of visible light. The darkness may dominate what we observe from far away, but the planet itself extends much deeper. Long before we reach anything resembling a center, physics predicts an immense internal structure shaped by pressures and temperatures almost beyond imagination. The outermost layer is the atmosphere itself. Here, hydrogen and helium swirl together with vaporized metals and the chemical compounds responsible for the planet's extraordinary appearance. This is the only region we can examine directly through spectroscopy, a method that studies how different molecules absorb specific wavelengths of starlight. Everything beneath remains hidden from direct observation, reconstructed instead through the laws of gravity, pressure, and planetary physics. But pressure transforms matter. As we descend farther inward, hydrogen encounters conditions exceeding approximately 1 to 2 million atmospheres. Under those immense forces, it undergoes a phase transition, meaning its physical behavior fundamentally changes. Instead of acting like an ordinary gas, hydrogen begins conducting electricity like a metal. Scientists call this state metallic hydrogen. It does not occur naturally anywhere on Earth, and researchers did not produce laboratory evidence for it until 2017, at Harvard University. Inside Jupiter, and almost certainly inside TRES 2b, this metallic hydrogen region forms the largest portion of the planet's interior. That layer does more than exist. Flowing electrically conductive material acts like a planetary generator. As metallic hydrogen moves through the interior, it can create a magnetic field through a process known as a dynamo, meaning the motion of conducting material converts kinetic energy into magnetism. Jupiter possesses one of the strongest magnetic fields in the solar system because of this mechanism. TRES 2b shares a similar overall composition while enduring far greater heating from its nearby star. Its magnetic field has not yet been measured directly, but current physics strongly suggests that it should be substantial. Farther down, another possibility awaits. Most formation models predict a dense core composed of rock, ice, or both. This core likely formed first, gathering material until its gravity became strong enough to attract enormous amounts of surrounding hydrogen and helium. Estimates for Jupiter suggest a core between 10 and 45 Earth masses. For TRES 2b, the exact mass and composition remain uncertain because no observation has reached that depth. But another puzzle appears. The measured radius of TRES 2b is approximately 1.27 times that of Jupiter, making it slightly larger than standard models predict for a planet of its mass and estimated age. This inflated radius has become a recurring problem among hot Jupiters. One proposed explanation is ohmic dissipation, a process in which magnetic interactions convert electrical energy into internal heat. Another possibility is tidal dissipation, where repeated gravitational stretching deposits energy deep within the planet. Those ideas reach back toward the atmosphere. If extra energy continually rises from the interior, it could sustain unusual chemical reactions high above the metallic hydrogen layer. In that case, the mysterious darkness surrounding TRES 2b may not originate only in the atmosphere we observe. It may also reflect processes unfolding far below, where immense pressure, magnetic energy, and hidden heat continue shaping the planet from within. There is another process unfolding above the cloud tops, one that does not build a planet, but slowly takes it apart. Around the hottest gas giants, gravity is engaged in a constant contest with heat. Over immense spans of time, that contest can remove part of the atmosphere itself. The process is known as atmospheric escape. When intense stellar radiation pours into the upper atmosphere, individual atoms and molecules gain energy. Some receive enough speed to overcome the planet's gravity entirely. Once they reach escape velocity, they no longer fall back. Instead, they drift into interplanetary space, becoming part of a gradual planetary outflow. This phenomenon has been predicted and observed around several hot Jupiters because of their close orbits and extreme temperatures. But gravity introduces another limit. Every orbiting world possesses a region where its own gravity dominates over that of its parent star. Astronomers call this the Roche lobe. You can think of it as the planet's gravitational territory. Material remaining inside that boundary stays bound to the planet. Material crossing beyond it is captured more easily by the star's gravity. Since TRES 2b circles so close to its star, its Roche lobe is comparatively compact, placing the outer atmosphere much nearer to this invisible boundary. We have already seen one clear example. The exoplanet named Hotel Delta 209458b became the first world where atmospheric escape was directly detected. Observations from the Hubble Space Telescope revealed hydrogen flowing away from the planet in a vast comet-like tail. Researchers estimated that approximately 10,000 tons of material were escaping every second. Even at that remarkable rate, The planet would survive for an extraordinarily long time because of its enormous mass. But TRES 2b remains less certain. Its temperature exceeds 1,000 degrees Celsius, or 1,832 degrees Fahrenheit, across the permanently illuminated hemisphere, while much of the opposite side also remains intensely hot. Under such conditions, atmospheric evaporation is considered highly probable. Yet no published measurements have determined the exact escape rate with confidence. The process is expected. The quantity remains unknown. That uncertainty carries an intriguing consequence. Hydrogen and helium are the lightest elements in the atmosphere. They escape more readily than heavier atoms and compounds. If this gradual loss continues across billions of years, the upper atmosphere could become relatively enriched in vaporized metals and other substances that absorb visible light with exceptional efficiency. Rather than creating darkness directly, atmospheric escape could slowly amplify chemical mixtures already present, increasing the concentration of the very materials suspected of suppressing reflection. But time becomes the deciding factor. The parent star is estimated to be approximately 5.1 billion years old, an age comparable to that of our own Sunday, that provides an immense span during which atmospheric escape could reshape the upper layers. Whether billions of years are sufficient to produce the extraordinary darkness we observe today remains unresolved. Once again, the evidence points toward a process that is physically plausible, scientifically consistent, and still incomplete, leaving another piece of TRES 2b's remarkable story waiting to be understood. Long before light reaches the atmosphere, another force has already shaped the space surrounding the planet. It cannot be seen directly, yet it influences charged particles across enormous distances. Every massive gas giant is expected to carry this invisible architecture with it, extending far beyond the boundary where the atmosphere ends. Its source lies deep inside. Within the vast layer of metallic hydrogen, electrically conducting material flows under tremendous pressure. As the planet rotates, those moving electrical currents generate a magnetic field through the dynamo effect, a process in which the motion of conductive fluid continually sustains planetary magnetism. This mechanism has been studied extensively within our own solar system, providing one of the strongest foundations for understanding the interiors of giant planets. Jupiter offers the clearest example. Its magnetic field is approximately 14 times stronger than Earth's. The surrounding magnetosphere, meaning the region dominated by the planet's magnetic field, stretches millions of kilometers into space, which is about hundreds of thousands to millions of miles, depending on direction. Within that immense region, charged particles become trapped, accelerated, and guided toward the poles, creating the most powerful auroras known in the solar system. But TRES 2b exists under harsher conditions. Its composition and mass strongly suggest that it also possesses a substantial magnetic field generated by metallic hydrogen. Directly measuring the magnetic fields of exoplanets remains one of the newest frontiers in planetary science. A small number of hot Jupiters have shown indirect evidence consistent with magnetic fields, yet no observation has definitively measured one surrounding TRES 2b itself. The prediction comes from physics rather than direct detection. The environment surrounding the planet makes that prediction especially compelling. At an orbital distance of approximately 5 million kilometers, which is about 3.1 million miles, TRES 2b moves through an exceptionally intense stellar wind. This continuous stream of electrically charged particles flows outward from the parent star at tremendous speeds. As those particles encounter the planet's magnetosphere, They are forced into complex motions, storing and releasing enormous amounts of energy. If auroras form there, they could exceed anything observed around Jupiter or Earth. But the interaction may reach even farther. Some theoretical studies suggest that extremely close, hot Jupiters can become magnetically linked with their parent stars. In this scenario, magnetic field lines connect the two bodies, allowing energy to move between them through direct magnetic coupling. Nothing comparable exists within our own planetary system. Such interactions could influence atmospheric heating, contribute to the enlarged sizes measured for many hot Jupiters, and alter conditions high above the visible atmosphere. That possibility returns us to the central mystery. Magnetic activity on this scale may change atmospheric chemistry in ways that standard models do not fully capture. It could transport material vertically between different atmospheric layers, sustain unusual chemical compounds, or create localized regions where temperatures differ enough to alter which molecules survive. The darkness surrounding TRES 2b may therefore reflect more than chemistry alone. It may also preserve the signature of an invisible magnetic structure that has shaped the planet for billions of years. If we pause for a moment, an important distinction begins to emerge. We know far more about TRES 2b than we did when it was first discovered, yet there remains a clear boundary between what has been measured and what has only been inferred. That boundary is defined by spectroscopy, the technique that allows astronomers to identify the chemical fingerprints carried within starlight. Some answers have already appeared. Observations are consistent with the presence of sodium and potassium in the atmosphere. Their broad absorption signatures match theoretical expectations for a hot Jupiter exposed to temperatures exceeding 1000 degrees Celsius or 1832 degrees Fahrenheit. These elements absorb visible light efficiently, making them natural contributors to the planet's remarkably low reflectivity. Their existence fits both atmospheric models and the brightness variations measured during repeated transits. But the list ends surprisingly quickly. Scientists have not determined the detailed abundances of individual molecules throughout the atmosphere. The precise vertical structure of clouds or haze layers remains unknown. No observation has conclusively identified an additional chemical compound capable of explaining why the planet reflects so little visible light beyond the effects already expected from sodium and potassium. The central mystery, therefore, remains exactly where it began. Distance plays a major role. TRES 2b lies approximately 750 light-years from Earth. By the time its starlight reaches our telescopes, the tiny atmospheric signal carried during each transit has become extraordinarily faint. Resolving individual molecular species beyond the strongest absorbers demands a level of precision far beyond what the original observations could provide. Each transit offers only a brief opportunity to collect that information before the planet moves away from the face of its star once again. But another limitation comes from the instrument itself. The Kepler Space Telescope was designed primarily as an exceptionally precise photometer, meaning it measured changes in overall brightness across one broad portion of visible light. That capability revealed that the planet absorbed an extraordinary amount of incoming starlight. It could not determine exactly which wavelengths disappeared. Spectroscopy approaches the problem differently by separating light into individual wavelengths, allowing specific atoms and molecules to reveal themselves through unique absorption patterns. Ground-based observatories have attempted that deeper investigation. Several transit spectroscopy studies have collected valuable atmospheric data, expanding our understanding beyond the original brightness measurements. Even so, the signal, compared with background noise, has remained too limited to reconstruct the complete atmospheric chemistry with confidence. Important clues have emerged, yet the unknown absorber responsible for the planet's extraordinary darkness has not been isolated. But the path toward an answer is becoming clearer. The James Webb Space Telescope possesses the sensitivity needed to perform high resolution transmission spectroscopy across broad regions of the optical and near infrared spectrum during multiple planetary transits. Such observations could reveal trace compounds that have remained hidden from every previous instrument. As of current scientific knowledge, no published investigation has yet provided the definitive spectroscopic evidence required to identify the unknown darkening agent, leaving TRES 2b as one of the most compelling atmospheric mysteries among all known exoplanets. A new observatory has changed what we can reasonably hope to learn from distant worlds. After years of relying on instruments that revealed only fragments of the picture, astronomers now possess a telescope designed to examine exoplanet atmospheres with a level of detail that was previously out of reach. For a world as enigmatic as TRES 2b, that difference could prove decisive. The James Webb Space Telescope was launched on December 25, 2021. Its primary mirror measures 6.5 meters, which is about 21 feet, far larger than the Hubble Space Telescope mirror, measuring 2.4 meters, which is about 8 feet. More importantly, it was built to observe primarily in the near infrared and mid infrared portions of the electromagnetic spectrum. The observatory also operates near the second Lagrange point, approximately 1.5 million kilometers from Earth, which is about 932,000 miles, where the combined gravity of Earth and the Sun helps maintain a remarkably stable thermal environment. That location matters. Many molecules leave their strongest signatures beyond visible light. Complex organic compounds, metal oxides, and atmospheric hazes often absorb infrared wavelengths far more effectively than optical wavelengths. The Kepler Space Telescope transformed our understanding by measuring extraordinary changes in brightness, yet it remained largely unable to identify these hidden chemical fingerprints because its observations focused on visible light. But the James Webb Space Telescope carries specialized instruments built for exactly that purpose. The near-infrared imager and slitless spectrograph, the near-infrared spectrograph, and the mid-infrared instrument work together to separate incoming light into extraordinarily detailed spectra. Spectra are simply light spread into its individual wavelengths, allowing specific atoms and molecules to reveal their unique absorption patterns. Instead of observing that light has disappeared, astronomers can determine much more precisely what removed it. During a planetary transit, another opportunity appears. As TRES 2b crosses in front of its star, a thin layer of its atmosphere filters a tiny fraction of the starlight before that light reaches the telescope. This technique, known as transmission spectroscopy, could reveal atmospheric molecules across an unprecedented range of wavelengths. Even a single, exceptionally high-quality transit may uncover chemical species that escaped detection during decades of earlier observations. But another method offers an equally valuable perspective. When the planet passes behind its star, an event called a secondary eclipse temporarily removes the planet's own contribution to the combined light. Comparing observations before, during, and after that eclipse allows astronomers to isolate the planet's infrared thermal emission. From that signal, researchers can estimate atmospheric temperatures, energy transport, and chemical composition with remarkable precision. Even so, an important limitation remains. As of current scientific knowledge, no published observations from the James Webb Space Telescope have definitively identified the unknown agent responsible for TRES 2b's extraordinary darkness. Yet the telescope has already detected water vapor, carbon dioxide, sulfur dioxide, and silicate clouds in the atmospheres of other hot Jupiters with unprecedented clarity. Those achievements suggest that the most compelling explanation for TRES 2b may not be beyond discovery, only beyond the reach of every instrument that came before. Long before astronomers measured the darkness of TRES 2b, people traced the surrounding stars into the shape of a great celestial dragon. If you were to stand beneath a clear northern sky and follow its winding path, you would be looking toward Draco, one of the oldest recognized constellations in recorded history. It was among the 48 constellations cataloged by Claudius Ptolemy during the 2nd century, giving this region of the sky a place in human memory that stretches back nearly 2,000 years. Yet Draco carries an even older connection. One of its brightest stars is Thuban. Around 4,000 years ago, while the ancient Egyptians were constructing the pyramids at Giza, Earth's slowly changing axis pointed almost directly toward this star. This gradual shift, called axial precession, is the slow wobble of Earth's rotation over thousands of years. Because of that motion, Thuban briefly served as the North Star, and passages within the pyramids appear to have been aligned toward its former position. But Draco extends far beyond the stories written beneath its stars. Looking into this direction also means looking through an astonishing depth of the universe. Part of the Hercules Corona Borealis Great Wall lies along this region of the sky. Discovered during 2013, this immense filament of galaxies stretches for roughly 10 billion light years, making it the largest known structure in the observable universe. The dragon, imagined by ancient civilizations, now shares its celestial neighborhood with a structure so vast that light itself requires billions of years to cross it. Closer to home, another remarkable object drifts through Draco. The Draco Dwarf Galaxy orbits our own Milky Way at a distance of approximately 260,000 light-years. It is a small satellite galaxy whose oldest stars formed only a few 100 million years after the Big Bang. When we observe those ancient suns, we are seeing survivors from one of the earliest chapters of cosmic history. Within this same constellation lies the star that hosts our extraordinary planet. It appears in the Kepler input catalog and later became known as Kepler 1, recognizing it as the first previously known exoplanetary system located inside the Kepler Space Telescope's primary observing field. That historical connection linked an already famous planet with the mission that ultimately revealed just how extraordinary it truly was. But you cannot simply walk outside and find it. The parent star shines at approximately 11th magnitude, far below the threshold of human vision. Even under excellent conditions, you need at least a moderate backyard telescope to detect the star itself. The planet remains completely beyond direct visual observation from the ground. That perspective changes something subtle. TRES 2b is not merely a collection of measurements inside a scientific database. It occupies a real place among familiar stars, inside a constellation watched for millennia, surrounded by ancient stellar populations and unimaginably large cosmic structures. Its remarkable darkness belongs to an address in the sky that humanity has followed, mapped, and contemplated across countless generations. Our view now widens beyond a single remarkable planet. As astronomers have surveyed thousands of distant worlds, a larger pattern has gradually emerged. TRES 2b occupies one extreme of that pattern, yet it is surrounded by other objects that challenge our expectations in entirely different ways. Together, they reveal that darkness itself is a recurring feature of planetary evolution rather than an isolated curiosity. Some planets never orbit a star at all. These are known as rogue planets, worlds that wander through interstellar space after being ejected from their original planetary systems through powerful gravitational interactions. Current estimates suggest the Milky Way alone may contain several billion such planets. Without a nearby star, they receive essentially no external illumination. Their surfaces or atmospheres, whatever form they may take, drift beneath the faint glow of distant stars. The first candidate rogue planet detected through gravitational microlensing, a method that finds distant objects by measuring how their gravity briefly magnifies background starlight. They was announced during 2011, the same year that TRES 2b's extraordinary darkness was confirmed. But another world demonstrates a different path toward planetary extremes. Kepler Input Catalog 12557548 B is a rocky planet orbiting so close to its parent star that its surface is steadily evaporating. Instead of presenting a stable silhouette during transit, it trails a vast cloud of dust resembling the tail of a comet. That drifting material blocks varying amounts of starlight, revealing that the planet is gradually losing itself. Here, darkness is tied directly to destruction. Objects even larger continue the pattern. Brown dwarfs occupy the boundary between planets and stars. They are too massive to remain ordinary planets, yet too small to sustain the continuous hydrogen fusion that powers true stars. They slowly release heat generated during their formation through gravitational contraction, causing them to shine primarily in the infrared rather than visible light. Their faint reddish glow comes from internal warmth instead of reflected starlight. In that sense, the thermal emission detected from TRES 2b represents a gentler version of the same underlying physics. But these comparisons lead toward a broader conclusion. Across our galaxy, nature repeatedly produces worlds that absorb light efficiently, emit mostly thermal radiation, or spend their existence almost entirely removed from visible illumination. TRES 2b remains the most extreme confirmed example of a highly reflective star being paired with an almost completely non-reflective planet. Yet it belongs within an expanding family of objects, demonstrating that planetary darkness is neither rare nor accidental. That realization reshapes how we think about planets. Our own solar system introduced us to brilliant icy moons, pale clouds, and giant planets striped with reflected sunlight. Exploring other stellar systems has revealed an astonishing continuum reaching all the way to the dim ember glow of TRES 2b. Between those extremes lies a diversity of physical and chemical environments that no observations of our own celestial neighborhood could ever have prepared us to imagine. Some worlds invite us to ask whether life might endure there. TRES 2b invites a different question. As we continue our journey, the goal is not to imagine possibilities beyond evidence, but to understand what the known laws of physics actually allow. In doing so, this remarkably dark planet becomes a valuable marker defining the outer limits of planetary habitability. Temperature provides the first and most decisive answer. Across TRES 2b, atmospheric temperatures approach 1,000 degrees Celsius or 1,832 degrees Fahrenheit. Under such conditions, liquid water cannot exist anywhere in the atmosphere or on any hypothetical surface hidden beneath its enormous envelope of gas. Water remains liquid only between 0 degrees Celsius or 32 degrees Fahrenheit and approximately 374 degrees Celsius or 705 degrees Fahrenheit, the critical point beyond which liquid and gas become indistinguishable. Every measured region of TRES 2b lies far beyond that physical boundary. But heat alone does not define this environment. As we descend deeper into the atmosphere, pressure climbs into the millions of atmospheres. These conditions exceed the greatest pressures found within Earth's oceans by many thousands of times. Under such immense compression, hydrogen transforms into metallic hydrogen, and exotic forms of matter become stable. Ordinary molecular structures struggle to persist. The intricate chemistry associated with biological systems cannot survive in an environment where atoms are continually forced into radically different physical states. Radiation adds another powerful constraint. Orbiting only about 3.1 million miles from its parent star, TRES 2b receives approximately 3,700 times more stellar energy than Earth receives from the Sunday. That relentless bombardment floods the atmosphere with energetic radiation capable of breaking apart complex organic molecules far faster than they could naturally assemble. Even before chemistry could organize into greater complexity, the surrounding environment would continually dismantle those molecular structures. The planet's tidal locking changes the circulation, though not the conclusion. One hemisphere permanently faces the star, while the opposite hemisphere never experiences daylight. Between them lies a persistent atmospheric circulation that transports heat around the planet through powerful global winds. Yet, both the illuminated hemisphere and the perpetual night hemisphere remain dramatically hotter than temperatures compatible with the complex chemistry associated with life. The circulation redistributes energy, but it never creates a temperate refuge. That distinction is important. When scientists conclude that TRES 2b is not a candidate for life as we currently understand it, they are not limiting imagination. They are following measurable consequences of temperature, pressure, radiation, and atmospheric chemistry. Every observation points toward the same result. This world defines one edge of the habitable spectrum, showing us where familiar chemistry ceases to function. By studying planets that clearly fall beyond those limits, we sharpen our understanding of the rare environments where the opposite conditions, stability, moderate temperatures, and enduring molecular complexity, might someday allow life to emerge elsewhere in the universe. Looking back toward our own planetary neighborhood, TRES 2b becomes more than an extraordinary destination. It becomes a comparison that helps explain why the solar system surrounding you and me developed along such a different path. Sometimes the fastest way to understand something familiar is to examine an extreme version that followed another history entirely. Jupiter offers the clearest example. Resting far beyond the rocky planets, Jupiter has spent billions of years shaping the architecture of the solar system through its immense gravity. Many astronomers describe it as a gravitational vacuum cleaner because it can redirect, capture, or scatter comets and asteroids before they travel into the inner planetary region. The protection is not absolute, yet its influence has reduced countless potential impacts over immense stretches of time. Had Jupiter formed close to the Sun or migrated inward until it occupied an orbit resembling that of TRES 2b, the inner solar system could have developed very differently. Stable, rocky worlds like Earth may never have survived long enough for complex history to unfold. But this idea reaches beyond a single planet. Some planetary scientists have proposed what is often called the Jupiter barrier hypothesis. The concept suggests that a massive gas giant, located beyond the rocky planets, may contribute to long-term planetary stability, while systems dominated by a hot Jupiter close to its star could struggle to maintain broad, enduring habitable regions. The hypothesis remains under active investigation, yet it provides another reason why studying distant planetary systems helps us understand our own. The planets themselves also reveal how strongly environment shapes appearance. Jupiter reflects about one-third of the sunlight that reaches it, giving it an albedo near 0.34. That value is more than 850 times greater than the extraordinarily small reflectivity measured for TRES 2b. Both planets are dominated by hydrogen and helium, yet one displays bright ammonia clouds, while the other absorbs almost every visible photon that reaches its atmosphere. Orbital distance and temperature have transformed two related worlds into dramatically different expressions of the same planetary family. But another question remains. Evidence suggests that Jupiter and Saturn did migrate during the solar system's earliest history through a process known as the Grand Tack hypothesis, a model describing how their orbits shifted before reversing direction. That movement appears to have stopped before either giant reached the inner solar system. Understanding why that migration halted, while worlds such as TRES 2b continued inward, remains one of the central challenges of planetary formation research. The comparison even reaches Earth itself. Our planet has an albedo of about 0.30, created largely by reflective clouds, bright ice, and sunlit oceans. Small changes in that reflectivity influence the balance between incoming sunlight and outgoing heat, affecting global climate over time. TRES 2b represents the opposite limit, a planet that has surrendered almost every natural source of visible reflection. By examining that distant extreme, we gain a deeper appreciation for how delicate Earth's balance truly is, and how profoundly the arrangement of a planetary system can shape the future of every world within it. Distance is easy to recite, yet remarkably difficult to imagine. Saying that TRES 2b lies 750 light-years away sounds precise, but the number only gains meaning when we translate it into the scales of everyday experience. That translation reminds us how extraordinary every observation of this distant world truly is. A single light year is the distance that light travels through empty space in 1 year. Light itself moves at about 299,792 kilometers every second, which is about 186,282 miles every second. Over an entire year, that becomes roughly 9.46 trillion kilometers, which is about 5.88 trillion miles. Even at the greatest speed found in nature, crossing such a distance requires an entire year, but TRES 2b is 750 times farther away. Imagine driving without ever stopping at 100 kilometers per hour, which is about 62 miles per hour. You would continue through day and night, across generations beyond counting, and the journey would still require roughly 805 billion years. That span is more than 58 times greater than the current age of the universe. Human history becomes almost invisible beside such a timeline. Even our greatest spacecraft barely changes the picture. Voyager 1, the most distant object ever built by humanity, travels at approximately 17 kilometers each second, which is about 11 miles each second. Maintaining that speed without interruption, it would still need around 13 million years to reach the star that TRES 2b orbits. The vast gulf between stars remains almost untouched by our present technology. But distance also changes time itself. Every photon that revealed TRES 2b began its journey toward us 750 years ago. When that light departed, the early 14th century was unfolding on Earth. The Aztec Empire was being established, and the Black Death had not yet spread across Europe. Long before the Renaissance, before the printing press transformed communication, and before the first sustained European contact with the Americas, those same photons were already crossing interstellar space. Only after centuries of human history had passed did they finally arrive at a telescope orbiting our Sunday. That realization changes every observation we make. We have never seen trees 2B as it exists today. We see only the ancient record carried by light that has traveled for 7.5 centuries before reaching us. Yet those ancient photons have revealed an astonishing amount. From them, we have measured the planet's mass, radius, orbital period, temperature, approximate atmospheric composition, and astonishingly low reflectivity. We have reconstructed the outline of a world unimaginably distant using nothing more than faint starlight. But the deepest question remains unanswered. After everything that light has told us, the true cause of the planet's extraordinary darkness still waits beyond the edge of what those centuries-old messengers can reveal. Long before we understand an unfamiliar world, we first have to decide how to describe it. Science begins with careful language, especially when direct observation reaches its limits. In the case of TRES 2b, nearly every conclusion rests upon measured light rather than photographs, making the words chosen by astronomers almost as important as the measurements themselves. One of those words is albedo. Albedo is simply the fraction of incoming light that a surface or atmosphere reflects back into space. The scale runs from 0 to 1. A value of 0 would represent perfect absorption, while a value of 1 would represent perfect reflection. No naturally occurring planet has ever been measured at either extreme. TRES 2b, with a geometric albedo of approximately 0.0004, lies astonishingly close to the absorbing end of that scale. It occupies a region that had remained almost entirely theoretical before careful observations revealed its remarkable properties. But numbers alone never tell the whole story. When the Discovery team published its findings during the year 2011, the paper relied upon the restrained language expected in peer-reviewed science. Terms such as geometric albedo, phase curve, and best fit model described the observations with deliberate precision. Outside the formal publication, astronomer David Kipping described TRES 2b as truly an alien world. Both descriptions were correct. One communicated measurable evidence. The other translated that evidence into an image that people could immediately understand. Astronomy has relied on this balance for generations. Many of its most familiar names describe relationships with light rather than visible appearance. Dark matter earned its name because its gravity can be measured even though it has never been directly observed across the electromagnetic spectrum. Dark energy refers to the unknown influence inferred from the accelerating expansion of the universe. Dark nebulae appear as empty regions because dense clouds of dust block the starlight lying beyond them. In every case, darkness became a label for something understood through indirect evidence rather than ordinary vision. TRES 2b belongs within that tradition, although its darkness is fundamentally different. Unlike dark matter, it is not invisible. We detect its presence through repeated transits, changing brightness, and precise orbital measurements. Its darkness is physical and measurable, produced by an atmosphere that absorbs visible light with extraordinary efficiency. Photons arrive, interact with matter, and almost never return toward the observer. The mechanism behind that behavior remains incomplete, yet the measurement itself is remarkably secure. But perhaps the most valuable lesson reaches beyond this single planet. Scientific progress rarely comes from pretending every mystery has already been solved. It advances by defining uncertainty with increasing precision. Every observation of TRES 2b narrows the possibilities while leaving one central question unresolved. Rather than exposing a weakness in scientific understanding, that remaining gap provides direction. It identifies exactly where future observations, stronger instruments, and better theories should be aimed. In that sense, the darkness surrounding TRES 2b is more than an unanswered question. It is a carefully measured frontier, waiting for the next generation of discovery. Some discoveries end with an explanation, others become the beginning of a much longer investigation. After years of observation and careful analysis, TRES 2b still belongs to the second group. We have measured this remarkable planet with impressive precision, yet several of its defining characteristics continue to resist complete understanding. The first unanswered question reaches the heart of everything we have explored. What specific substance, or combination of substances, makes the planet so extraordinarily dark? Sodium and potassium absorb visible light, and theoretical models also consider compounds such as titanium oxide under certain atmospheric conditions. Those ingredients explain part of the effect, but they do not account for a geometric albedo of only 0.0004. Something else appears to be participating in the process, and its identity remains unknown. But the atmosphere may have been changing for billions of years. If TRES 2b is gradually losing part of its upper atmosphere through atmospheric escape, lighter gases could slowly disappear, while heavier, light-absorbing materials become relatively more abundant. That possibility has not yet been tested with the dedicated spectroscopic observations needed to measure the process directly. Until those observations exist, the idea remains a plausible explanation rather than an established conclusion. Another uncertainty lies farther away. The nearby stellar companion, identified close to the host star, has not been definitively confirmed as gravitationally bound to the system. If it truly shares the system, its gravity may have influenced the planet's orbital evolution long ago. If it does not, an entirely different history must be reconstructed. That distinction matters because planetary migration often depends upon the gravitational relationships established during the earliest stages of formation. The invisible environment surrounding the planet raises another question. Gas giants are expected to generate magnetic fields through the motion of metallic hydrogen deep inside their interiors. Yet, measuring the magnetic field of an exoplanet remains among the most demanding challenges in modern astronomy. If TRES 2b possesses an unusually strong magnetic field, interactions with the stellar wind could influence upper atmospheric chemistry in ways that existing models only partially describe. But perhaps the most anticipated answer depends upon our newest observatories. The James Webb Space Telescope possesses the capability to investigate planetary atmospheres with extraordinary sensitivity across infrared wavelengths. As of the current scientific literature available during the preparation of this documentary, no published observations have definitively identified the unknown agent responsible for TRES 2b's exceptional darkness. Future analyses may change that picture, but they have not yet done so. Stepping back, one final observation becomes impossible to ignore. TRES 2b was discovered during the year 2006 and its extraordinary darkness was confirmed during the year 2011. More than a decade of investigation has followed. The persistence of this mystery does not reflect a lack of effort. Instead, it marks the true edge of present knowledge. Sometimes science advances by collecting answers. Sometimes it advances by defining the remaining questions with such precision that the next generation of instruments knows exactly where to look. Knowledge usually begins with light. We point a telescope toward the sky, gather faint photons, and slowly assemble a picture of something unimaginably distant. Yet, TRES 2b presents a remarkable contradiction. We know its orbit, its mass, its approximate atmosphere, its temperature, and its astonishing darkness. Every one of those discoveries comes from light that traveled across space for centuries. A planet defined by absorbing almost everything that reaches it has revealed itself through the tiny fraction of light it does not completely consume. That contradiction reaches deeper. Science often advances by studying what is missing as carefully as what is present. An absence can become evidence when it refuses to fit expectation. On TRES 2b, the missing ammonia clouds matter because they should have brightened the atmosphere. The missing reflected light matters because ordinary gas giants return far more of the light falling upon them. The missing chemical explanation matters because every successful atmospheric model leaves a small but persistent remainder that has yet to be understood. These gaps are not empty spaces in our knowledge. They are measurements pointing toward discoveries that have not yet been made. But this relationship between darkness and mystery did not begin with astronomy. Across civilizations separated by continents and centuries, darkness has often represented the unknown. It became the setting for myths, cautionary stories, spiritual journeys, and unanswered questions. Human imagination naturally filled unseen places with possibility because there was little else to work with. TRES 2b occupies an unusual meeting point between those ancient instincts and modern science. Its darkness is neither metaphor nor illusion. It is measurable, repeatable, and confirmed through careful observation, even though the complete explanation continues to elude us. The universe, however, makes no distinction between what feels familiar and what feels impossible. Under the right temperatures, pressures, and chemical conditions, matter behaves exactly as the laws of physics require. TRES 2b is one expression of those laws. Another planetary system, built from different initial conditions, naturally arrived at an outcome unlike anything in our own neighborhood. From that wider perspective, the planet is not an extraordinary mistake. It may represent one of many possible destinations reached by ordinary physical processes operating across billions of years. But that realization gently shifts our perspective. Perhaps the unusual place is not TRES 2b at all. Perhaps the rare arrangement is our own solar system, where giant planets remained far from the sun, reflective clouds formed within cooler atmospheres, and a small rocky world developed oceans beneath a sky that scatters blue light. We naturally compare every distant world to our home because it is the only example we have ever inhabited. Seen through that lens, the darkness of TRES 2b becomes a form of completeness rather than deficiency. Nothing about the planet is unfinished or broken. Its atmosphere absorbs light because its chemistry and environment permit exactly that outcome. Earth reflects sunlight from clouds, oceans, and ice for equally natural reasons. Both worlds obey the same universal rules. They simply reveal different possibilities hidden within them. Long before telescopes transformed the night sky into a map of measurable worlds, people looked into its darkest regions and imagined stories. Empty spaces between bright stars became passages, rivers, creatures, or openings into distant realms beyond ordinary sight. What could not be explained invited interpretation. Darkness was rarely accepted as simple absence. It became a canvas where each culture painted its own understanding of the universe. Centuries of observation gradually changed that picture. Many of the dark shapes, once surrounded by legend, are now known to be immense clouds of cosmic dust. They block the light of more distant stars, creating silhouettes against the brighter background of the Milky Way. The darkness remains real, yet its meaning has changed. Better instruments replaced inherited assumptions with evidence, while reminding us that every generation begins by interpreting what it cannot yet fully observe. But TRES 2b introduces a different kind of projection. Its darkness cannot be seen directly with human eyes. Instead, it appears through measurements, models, and tiny variations in starlight. Faced with an explanation that remains incomplete, researchers naturally approach the puzzle from different directions. Atmospheric chemists examine molecules capable of absorbing visible light with extraordinary efficiency. Scientists who study planetary magnetic fields consider whether invisible magnetic interactions could influence the upper atmosphere. Experts in planetary formation look farther back, asking whether the planet's migration through its own system shaped the chemistry we measure today. Each perspective contributes valuable evidence, yet each also reflects the questions that particular field has learned to ask. That pattern reaches beyond a single planet. Whenever astronomy encounters something unexpected, an important choice appears. Do we continue refining existing explanations, or do we ask whether the underlying framework itself requires adjustment? History offers many examples where the second path changed our understanding of the universe. The discovery of hot Jupiters challenged earlier ideas that giant planets always formed and remained far from their stars. Planetary formation models expanded because observations demanded it. TERS 2b may eventually play a similar role for atmospheric science if future evidence reveals processes that present models cannot fully reproduce. But there is also a deeply human perspective. You and we belong to the first generation that knows this world exists at all. Less than 2 decades ago, TRES 2b had no place in humanity's shared knowledge. For thousands of years, countless observers looked toward the winding stars of Draco. Sailors, philosophers, farmers, and astronomers all saw the same region of sky. None could have imagined that approximately 750 light-years away rested a gas giant, darker than coal, circling a star much like our own, while giving off only the faint glow of its tremendous heat. That knowledge now belongs to our species because a small group of scientists measured tiny changes in a distant star's brightness with extraordinary patience. Their work did more than reveal another planet. It expanded the boundaries of what humanity knows exists. TRES 2b reminds us that every unknown world first enters history not through certainty, but through the willingness to keep looking where darkness seems to reveal almost nothing at all. Imagine, for a moment, reducing an entire planet to a single point of color. Not blue like Earth, nor striped like Jupiter, nor wrapped in golden clouds like Saturn. Instead, picture a dim red spark suspended within an immense darkness. That is the image TRES 2b ultimately leaves with us. After every measurement, every calculation, and every model, what remains is a world that almost refuses to shine, yielding only the smallest glow that its own heat cannot suppress. Its warmth guarantees that faint light at approximately 1000 degrees Celsius or 1832 degrees Fahrenheit. The planet cannot become completely invisible. Matter at that temperature naturally radiates energy. Even after swallowing almost every ray of visible starlight, TRES 2b continues to emit a soft infrared glow and the slightest hint of deep red thermal light. Physics allows no less. It is a reminder that complete darkness remains just beyond reach, even for the darkest planet we have ever measured. But that lingering glow carries another meaning. An ember is the final trace of a fire, still holding energy long after bright flames have disappeared. TRES 2b feels strangely similar. Long ago, it almost certainly formed far from its parent star, where giant planets are expected to emerge from cold clouds of gas and dust. Over immense spans of time, gravity drew it inward. Extreme heat reshaped its atmosphere. Reflective clouds disappeared. Chemistry changed. Today, we find a giant world that has settled into a stable existence, absorbing nearly everything that falls upon it while continuing to glow with the leftover heat demanded by its environment. Its journey has been unimaginably long. For billions of years, the same hemisphere has faced its star, while the opposite hemisphere has faced open space. Long before Earth produced forests or flowering plants, TRES 2b had already reached this enduring state. Entire branches of life appeared and vanished on our planet, while that distant gas giant completed one orbit after another, circling its star every 2 days and about 11 hours without interruption. But its heat became more than a consequence. It became a message. That faint thermal emission contributed to the delicate changes recorded in the brightness of its parent star. Those tiny variations helped astronomers understand the planet more completely than reflected light alone could have allowed. In an unexpected way, the intense heat trapping TRES 2b within its extreme environment also gave it a detectable voice across approximately 750 light years of space. So perhaps this is the image worth carrying with you. A world nearly the size of Jupiter, blacker than any planet known in our own solar system, faintly red because it cannot cool enough to disappear. Locked forever between relentless starlight and endless night, circling a star it will never leave. Deep within that scorching atmosphere, some still unnamed combination of matter continues to absorb almost every visible photon that arrives. Across centuries of traveling light, that distant ember reaches us, asking nothing, revealing only enough for us to know it is there, while keeping one final secret hidden within the dark. There is a remarkable question waiting beneath every measurement we have explored together. It does not belong only to TRES 2b, it belongs to us. How much of the universe do we truly understand when a single planet, about 750 light years away, discovered less than 20 years ago, and examined with one of the most precise space telescopes ever constructed, still contains a chemical mystery beyond our present explanation? That question deserves patience, but its scale becomes even greater when we widen our view. TRES 2b is only one among more than 5,700 confirmed planets beyond our solar system. Those worlds orbit within a galaxy containing an estimated 200 billion to 400 billion stars. Beyond the Milky Way lies an observable universe holding an estimated 2 trillion galaxies. Against that backdrop, the unexplained darkness of one distant gas giant stops looking like an isolated puzzle. Instead, it becomes a reminder that our current understanding samples only a small fraction of the possibilities that nature has already produced. That realization carries humility. It also carries hope. Unlike mysteries of the distant past, this one has clear boundaries. We know the planet's mass. We know its radius. We know the length of its year. We know its approximate atmospheric temperature, around 1000 degrees Celsius or 1832 degrees Fahrenheit. We know its extraordinary reflectivity with remarkable precision. Each measurement narrows the space where the answer can hide. A well-defined mystery invites better observations, stronger atmospheric models, and new ideas that future instruments can test against reality. But the value of TRES 2b extends beyond its own atmosphere. Whatever eventually explains its remarkable darkness will influence our understanding of thousands of other giant planets. Every improvement in atmospheric chemistry, cloud physics, or planetary formation expands far beyond a single world. One solution becomes a foundation, the next discovery grows from it. That has always been the rhythm of astronomy, each answer revealing another horizon instead of closing the journey. If you were to look toward the constellation Draco tonight, you would never see TRES 2b with your own eyes. Between you and that faint ember stretches about 750 light years of space. Yet that immense distance has not prevented human curiosity from reaching it. Through careful observation and patient analysis, we have learned that such a world exists, despite its refusal to reflect almost any visible light. Perhaps that is the deepest lesson. The same curiosity guiding astronomers toward a planet measured to 4 decimal places is the instinct that once encouraged people to follow unfamiliar coastlines, navigate by the stars, and wonder what lay beyond the next ridge or sea. Every generation inherits a different frontier. Ours reaches across the galaxy toward places almost impossible to see, where even darkness itself becomes something we can measure, question, and slowly begin to understand. We have traveled a very long way to return to the question that first drew us here. What do scientists think is hiding inside the darkest planet ever found? The most honest answer is also the simplest. Something we have not yet identified, perhaps a single compound, perhaps a combination of atmospheric chemistry, unlike anything our present models predict. Whatever the answer proves to be, it will not overturn the laws of physics. It will reveal another way those laws can express themselves, under conditions far removed from anything our own world has ever known. But astronomy has always advanced this way. Again and again, observers have discovered phenomena that appeared long before they could be explained: a strange orbit, an unexpected spectrum, a faint signal hidden within distant light. The evidence arrives first, understanding follows later, sometimes years afterward, sometimes generations later. TRES 2b now belongs to that long tradition. Its darkness is not a flaw in scientific knowledge. It is a carefully measured frontier, waiting for sharper instruments, better atmospheric models, or a completely new insight that connects pieces we have not yet learned to assemble. That patience is part of the process. As our telescopes improve, each new observation will narrow the possibilities. A future spectrum may isolate the missing absorber. A refined atmospheric simulation may reveal chemistry overlooked today. Another mission may measure properties that remain beyond our current reach. The mystery will not last forever. Yet its resolution will almost certainly raise new questions, because every solution in astronomy opens another door beyond it. But TRES 2b itself remains unchanged by our curiosity. For billions of years, it has completed the same swift orbit around its star. Its days have passed without seasons. Its atmosphere has continued absorbing nearly every ray of visible light that reaches it. Its own heat has remained enough to produce a faint, reddish glow, even while almost everything else disappears into darkness. Long after tonight has become another memory, and long after every human lifetime now unfolding has ended, that distant world will most likely continue along the same path. There is something steady in that thought. If you could stand beneath the northern sky on a clear night, the constellation Draco would continue its slow passage overhead, just as it has for countless generations before us. Hidden within that familiar pattern, about 750 light years away, that is nearly 4.41 trillion miles, a giant planet circles, a star we cannot see without powerful instruments. It remains blacker than coal, hotter than a furnace, and still unnamed in one important way. Somewhere within that extraordinary atmosphere, matter interacts with light through chemistry we have yet to understand. The universe does not hurry to reveal its answers. It simply waits for observers patient enough to keep looking.